McFassel. I'm a current postdoctoral researcher here with RCPS at TU Darmstadt, and I'm here to talk to you today about plan-based approaches to robot design. Oops. Sorry. So this will be covering work I did during my PhD, but also I'll be covering some work done by other people that might be of interest to those of you in robotics. So we'll get started with it. So this talk is going to be broadly broken up into two pieces. Conveniently, both of them are in the title. The first is, what is robot design? What do I mean when I say that? And why should we care about what I mean when I say it? And second, what does it mean for something to be plan-based? What do I mean by a plan in this context? And how do plans apply to designing robots? So to answer that larger question of how we design robots and what plan-based means, I'm going to start with an easier question, maybe. What is a robot exactly? Most of us know a robot when we see it, so it seems like it should be pretty straightforward to answer. I put up on the slide a couple different robots. We have Pepper, which is from SoftBank and is used for interacting with customers. We have Spot, a research platform, and we have an original 2002 Roomba, which is a vacuum. What makes these robots, though? Is it that they have sensors and actuators? Maybe it's some notion that they have an internal state of the world. Or maybe it's their ability to perform computations. These all seem pretty reasonable at first glance. But there are exceptions to every category. So if we require onboard sensors, we're going to immediately disqualify many successful multi-agent applications, such as a lot of RoboCup teams, such as this one here, which doesn't quite seem right. For actuators, it depends on how strict you want to be, but we can at least agree probably that this origami crane that's actuated by heat applied to the system is at least non-standard. When it comes to internal state, again, the first Roombas had no they were purely reactive systems. They simply went along in a line until they bumped into something and then changed direction. And if we want even computational ability, this is a robot from UC Davis. It's made from thread and special materials. And it has the ability to move and bump into obstacles and change direction and then keep going. So it has no onboard computers. So while we initially might think that a robot is something like this, a machine that gathers information, performs computations, and chooses responses, we actually see that it's not quite so clear in many cases. And so you end up with some definition kind of like this. Sometimes they use sensors, sometimes they do computations, sometimes they do actuation responses. And as you've probably immediately realized, this is not a useful definition of a robot. It is so broad as to tell us nothing about what robots are or what they do. So this gives us a bit of a problem. What is a robot? Robotics is a massive research area. It's a huge industry, and yet nobody seems to know exactly what a robot is. We lack a formal theory for many conceptual questions in robotics, and this is a pretty big gap that we face. Other areas such as control, kinematics, and algorithms have managed to develop formal theories that allow for the discussion and precise understanding of wildly different systems and the comparison of how they're implemented, even when the underlying mechanisms may be completely different. And yet robotics really lags in this area. And this isn't just a conceptual annoyance either. This prevents us, as people who want to work with robots, from being able to answer some pretty significant questions, such as, what does a robot even have to learn? What capabilities does it have to have? And what can the robot actually do successfully? So, as a way to answer some of these questions, instead of focusing on a precise definition of what a robot is, let's instead focus on the following. Robots are machines we build to serve a purpose. That purpose can be quite varied, and so it's almost impossible to reconcile all of those purposes under a single definition of what a robot is or has to be. But we can consider robots by how well they do the things we want them to do. Instead of looking at sensors or actuators, looking at the purpose we've assigned them and whether they achieve it and how well they do so. So this brings me to the talk overview. I said earlier there were two parts. I lied, there's three. The first part will be how do we design robots? And specifically, I will be looking at the realm of theoretical robot design. Specifically within that, I will be looking at abstract sensing, and I will be discussing what abstract sensors are and how they help us design real robots. And then we will go into the plan-based approaches to robot design, wherein I will cover what I mean when I say plan-based, why we should consider plans for robot design, and how we do that. And then, depending on time, we'll go into examples. So, without further ado, how do we design robots? So, as we've already seen in the initial examples, the technology that robots incorporate varies quite a bit. So any approach we have should not consider that. So I propose theoretical robot design. Well, not me specifically, this is a branch, but in this talk, I propose theoretical robot design as a contrast to specification-based approaches, where you have a master student go out with a task and they come back with a bill of parts for a robot you need to build, or you see what parts you can actually afford or what parts you have in the lab and you put a robot together like that. This is often how we see robots actually get built. It's not super helpful for understanding how robots work or what they do. Theoretical approaches should be technology agnostic, and in specifically, I'm looking at information-based approaches. So how does a robot obtain information? And then how does that robot use information to enact changes on the world? So theoretical approaches allow for a couple things that we don't get when we're simply trying to design robots to a specification. They allow for us to answer questions such as determining if an arbitrary robot is capable of completing a task, comparing completely different robots, for example, this wheeled robot and this robot with what I tried to draw as propellers, seeing what they have in common, what they can achieve, what they can't achieve, and understanding where those tasks differ. And the focus of today's talk will be considering it, making decisions about robots before we've even implemented them. So when we're still in the design stages of a robot and we're trying to understand how to actually go about designing it to perform the tasks we want, how do we actually think about these problems? And the way that we achieve that is theoretical sensors. So inevitably, the first question I get when I say that I'm interested in theoretical sensors is, what is a theoretical sensor? Sensors are very concrete things, after all. You can look at the image from a camera, or you can watch a LiDAR, or you can look at the 3D map that a LiDAR produces, or you can watch a Roomba smack into a wall with its bump sensor. But the image from a camera is, of course, just an array of data from individual sensors, and it depends on the fidelity of the camera for how good that image is. A Roomba's bump sensor is just a button with a spring attached to it. We tend to think of sensors as having a one-to-one correlation with the information they provide, and we gloss over the sort of mental tricks we do to make this consistent in our own minds, like thinking of cameras as providing images, or even saying that a sensor is capable of detecting a bump. But this is actually just an abstraction. And so to give you a better idea of what a theoretical sensor is, which is most sensors, I'll go through another quick example. So say we take this camera and we feed its output into a neural network or what have you. This camera captures RGB sensor data, like I said, and then we give it to this network, and our neural network returns a yes or no answer depending on if it detects the face of a user within the frame. We might consider that we have a face sensor, something capable of detecting faces, because that's the ultimate outcome of this object, despite the fact that no part of the system is actually independently capable of detecting a face and returning that as data. Furthermore, the precise type of camera we have here and the exact weights of the neural network that return this information aren't actually particularly relevant to our purposes, so long as they give us that ultimate piece of information we need, whether or not there's a face. So this is essentially the essence of theoretical sensors. Theoretical sensors indicate what information is available to a robot, what it can actually learn from the environment. They make no claims about how that information is received or what you do with it after you get it. And this is sort of how they provide a foundation for robot design, because they're great for problems where we know we can get information, but we don't actually want to commit to how that information is received yet, like robots. So to sort of make this a bit either more concrete or less concrete, I'm going to go through a couple of different examples in the literature of theoretical sensors, talk a bit about how they work, and hopefully you'll understand the concept by the time we get on to the next part. So for the first example I'm going to present is this work on Bayesian networks for path-based sensors. So if you're interested in any of these papers, the citations are at the bottom. I highly recommend checking all of them out. They're all quite cool. But we'll start with this work that covers just how abstract theoretical sensors can be. So imagine you have a group of robots exploring the world, and each robot goes along a different path, and it returns back to base when it successfully completes that, or it encounters some misfortune along the way and it doesn't come home. Now, these individual robots can be quite simple. In fact, all they need is enough sufficiency to follow a path. But the return or failure to return of these robots provides information to the collective that can direct their behavior and their future path planning. We can consider this information a kind of hazard sensor, despite the fact that no such thing as a hazard sensor has ever existed or will ever exist. The point here is that information comes from sensors other than information comes from sources other than sensors built into the robots. In this case, a hazard sensor, but not in many other cases, it can be much more abstract. The second point I want to make with theoretical sensors, we'll look at gap sensors. So gap sensors are essentially if you have a robot capable of detecting distances from it in a circle, you can detect discontinuities in depth, which tells you that there's a gap in the environment. Navigational algorithms and mapping algorithms exist for these kinds of sensors, but a gap does not exist in the world. It is purely an experiential phenomena wherein a robot in a certain position is getting a certain reading. If we move this robot in between this orange and blue shape, it will experience this gap as a completely different part of its space. But theoretical sensors allow us to capture this information that is experiential. It's not purely limited to what we can actually detect, but it includes what we can learn and what we experience. And then, most importantly, theoretical sensors allow us to get quite broad about what a sensor is allowed to be. And this can be very useful for us as designers and for the rest of the talk. So our final example, and most relevant to this work, is Michael Erdmann's 1995 paper, Understanding Action and Sensing by Designing Action-Based Sensors. This goes further than our previous examples and states that sensors should actually only give actions. Sensors should just tell a robot what to do next. For example, a robot might ask its sensor for a reading. Where am I? Reasonable enough. And the sensor tells you, oh, you're at go right. And this might sound quite strange for a sensor to give us actions as opposed to any information about the environment, but this framework can be a powerful tool for actually understanding what we need to learn about environments in order to guarantee test completion. So consider this example here. We have a robot in the upper left corner, and it wants to get to the flag in the lower right. There exists this single obstacle in the space, and our robot can either move down or to the right. So we see that there are different regions of the space where one motion of it is effective and the other is not, namely around the obstacle on the edge of the arena. So our robot needs to at least identify enough about this world that it doesn't get stuck. Now, in Erdmann's original paper on this, to obtain an action-based sensor, you begin with a plan. These plans in this work were obtained from backchaining from the goal. So one example of a plan looks like this. On this plan, you can then define a progress measure. Progress measures indicate how far a task is from being completed. They are real valued functions on the state space, in this case, on our grid world. And progress is defined as moving from a high valued space to a low valued space. Oops. So the progress measure equals 0 at the goal. And then as we go further away from the goal, our progress measure takes higher and higher values. We use a simple Manhattan distance metric here. You can kind of use whatever you want. By defining this distance metric, we can then define progress-making actions, and therefore identify regions of the world where certain actions make progress under this definition. So you can see down here at the bottom row, going right always makes progress, or yes, on the right side, going down always makes progress, and so on. This gives us a partition of the space into regions where one of these two actions makes progress. And this defines a specification for a sensor. All you actually need to recognize about this world is enough to know which of these partitions you're in and when you've reached the goal. That's it. So you only need to know if you are in go right or if you are in go down. If your goal is simply to make it to the goal, no other information actually matters. But this choice of this plan was to some extent arbitrary, right? You could just as easily have made a plan that looks like this or a plan that looks like this. And what we see here are two things. One, there are areas where there are arbitrary choice in action and it doesn't actually matter. But we might want to preserve that multiplicity of choices and not lock ourselves into only being able to go right or only being able to go down. So there's a bit of annoying incompleteness there. And second, there are regions such as the bottom and the right side where you do have to commit to a certain action. And we would also like to know, in all cases, where these regions are. So if a sensor can just tell us what our robot should do next, that's great. That's really actually all we want robots to ultimately know is what action they need to take next. But that does leave us with some questions. Namely, is that all? Like you saw, Erdmann used very specific plans, those obtained via backchaining to obtain sensors. But we just saw there are other types of ways of specifying robot behavior. What happens if we want to preserve choice in action? Or what happens if our robot's required behavior is too complex to be expressed purely reactively? What if we know ahead of time that we're going to need to learn things about the environment, or even that we want to accommodate multiple different goal states that we could be in? To obtain additional action-based sensors, we need to know how information learned affects task completion and how our prior actions impact our future decisions. We have to link what a robot sees to what it does next, as well as what a robot does later to what it has accomplished before. Conveniently, there is already a very common branch of robotics that tackles just what robots should see and do in those cases, and that's planning. So, before we get on to the second part of the talk, I'm actually going to take a brief intermission because it's actually quite important that you understood all the concepts of action-based sensors and things here. So if anyone here has a question, or if anyone viewing online has a question, I'll take them for like maybe 2 minutes before we go on. And if not, I'm going to assume you understood everything perfectly. Oh, sorry, yes.
How do we deal with sensors that are not one sensor? So maybe two temperature sensors that we use for noise reduction or something like that.
Oh, that's a really good question. I will be able to answer that probably a bit better when we get into the second part, but essentially the idea is what we're going to look at in the extension to this theory is that we just take essentially just like input strings for observations. So those input strings could be almost anything. They could be sequences, they could be sets. We don't have any limits on that. In Erdmann's original work, they're usually just distance metrics, so you would just have some different information. But the idea to this, to some extent, would be, let me answer. The idea to some extent is that, you know, we're trying to answer this with just a single sensor, and then if it fails with just a single sensor, then you can look at adding additional information. But also, yes, the model that we'll be looking at accommodates multiple inputs. Any other questions? Okay, so I'm going to assume everyone understood that perfectly, and we are going to get into part 2, plan-based approaches to robot design. So as I said at the end of this previous section, why focus on plans and planning problems? Well, planning is a really mature area of robotics. There's an enormous body of existing work on how to model planning problems and plans, and how to use methods to make plans faster, more robust to failure, more optimal, you name it. But despite this, we often think of plans as something that we're finding. Often we implement planners to find a plan, and then we just take the plan and we say, okay, we're good. We often don't consider what plans actually tell us about the problems that they're solving. But planning problems and plans tell us a lot. They're expectations for what observations we actually believe we're going to see. They tell us what actions the robot's allowed to take, and they give structure to how sequences of events are actually allowed to occur. Meanwhile, plans are behavioral specifications for the robot itself. And as we said previously, determining what a robot needs to sense depends on how we expect it to behave. So plans also link this interplay between what robots see, what they've done before, and what they'll do next. So given that we can have arbitrary plans defined for arbitrary planning problems, we'd like to use them to develop all action-based sensors, not just those obtained via backchaining. We want to include ones we couldn't previously handle, such as those that suffer uncertainty in their state, or those that have memory requirements. And we'll also see that we can use action-based sensors to solve design problems that we care about. Oops, I'm gonna hit my laptop. So just to sum up kind of what I said on 3 slides there, planning problems are descriptions of the world, right? They have states, they have observations, they have actions. A plan is a description of behavior. We can think of a robot executing a plan as a game being played between the world and the robot. The robot receives observations chosen by the world and takes an action in response. This changes the overall state, the robot receives new observations, the game goes on. So we can make this relation quite precise through a bipartite directed graph, which we call p-graphs. You can read the paper on it if you want. But essentially, these are a discretization of the world into a bipartite directed graph structure. We have vertices with edges connecting them, which yield observations and actions. We have a goal, and we have some starting vertices, which can be any or all observations in the world. They can also be actions, but in this case, we're just looking at observations. So we have the world here, which issues an observation, oops, and we have the robot's action in response, and they trade off making decisions until the end of time, or you get to the goal. The plan is also a bipartite graph structure. It has vertices with edges connecting them, which yield observations and actions. It has a location where it terminates, and it has some starting vertices. So plans solve planning problems if they play nicely together. They have finite executions, and they're always ready for what the world can give them. So we have here just an example. You can see the plan on the right, the planning problem on the left. And as we go through and receive observations and take actions, our state changes both in the world and in the plan. This example is actually not a valid solution to this planning problem, as this action here can actually take us back to the start non-deterministically. I left this in to highlight that problems in this space can have non-determinism. We can have actions that lead us to uncertainty in states. And we can also have a robot that sort of occupies multiple states in the world at the same time, which correspond to a single point in the plan. The examples we'll be looking at in this talk are fully observable, so we'll always know where the robot is more or less. But it's important to realize that the definition doesn't require this. And just to go back to your question, because these observations are arbitrary, we can just make them strings of any type. You perform intersection operations to enforce consistency between these two. Okay, so let's take a look at a pretty basic example that we will be looking at a lot for the next couple slides. And then we're going to take a look at some arbitrary plans that we'd like to develop action-based sensors for. So here's a robot in a very basic little world. Only 7 distinguishable regions as indicated by these dotted lines, and 2 obstacles marked by circles, and a goal marked by the letter G. Our robot here can move between adjacent cells and go wherever it wants, essentially, throughout this entire world. So now let's take a look at 2 plans. Our robot could theoretically start anywhere in the world, but just to make this easier, we're going to say in these instances, it started on the left side. It then randomly picks one of these 2 plans to execute. So it can either go like this, or it can go like that. can either do a little S or a little Z. Here, S. Now, assume that we want to take these plans and define a progress measure as we did previously so that we know what actions take us towards the goal. Not unreasonable, right? But we see pretty quickly that there is no consistent ordering that accommodates both of these movement patterns. The ability to have choice in our actions has led to an inability to place a single ordering on the states of these worlds. And this means the resulting plan lacks a progress measure. We call this phenomenon a crossover because the paths kind of cross over each other. It will become slightly clearer in a moment. But what do we do about it? Well, let's take a closer look at the problem by making it a bipartite graph. So if we want to model the world in our p-graph structure, we might start with something like this, a single observation and action for every state in the world. Now, if we were to create a plan for the top path, we could make one that looks like this. And if we want to create a plan for the bottom path, we can make one that looks like that. And if we consider them simultaneously, we'll see that now together, they look like this. And now you can see why it's called a crossover. The paths cross over and they form a cycle in the graph. I like it. But just because we have a cycle in a graph that I constructed on this slide doesn't mean that such a cycle exists on the original plan. In fact, it can't definitionally because the plans have finite languages. Our original plan probably looks a little closer to this. We start with a random choice at the beginning of execution. We take it as a couple actions on these isolated paths, and we visit these plan vertices that correspond to these parts of the world in different orders. So we've got a bit of a problem here. Cycles like this prevent progress measures from being defined, but these cycles only exist in the abstract. They only are discoverable when we know the precise way in which plan vertices correspond to the worlds on which plans act. So how do we identify these cycles? And more importantly, what do we do about them once we've found them? So, like I said, the problem's they're cycles. So we need to find and clip them. So I'm going to talk a bit now about an algorithm that I developed during my PhD called CLIP. CLIP is an algorithm that identifies these cycles in behavior, and then it procedurally resolves them to get us all possible action-based sensors. So to identify how a plan's behavior results in cycles in the world, we need to translate that plan's behavior into a new structure, one that makes these links between behavior and the actual world on which the robot operates explicit. Here's an example that uses a world W. We see our one plan, we see our other plan, we kind of smush them on top of the original world, and we see these cycles. But you can't do this for quite a lot of problems, because this only works if you know exactly how the plan and world map to each other, and often there's uncertainty that the original plan has. So we need to understand how the plan moves through the world and what information it gathers. So to do this, we build a structure called the plan world interaction graph, or simply the I-graph or interaction graph. And it works a bit like this. So before I play this video, I'll start the spiel. As we ultimately want to obtain a sensor specification from this, we need to eliminate, like I said, any advantages that our robot might get from starting in a certain place in the world. So we're going to assume we can start anywhere, and we'll mark this with a special diamond vertex. And then we will generate some states. So we see here we have a box for each state in our original world. And in the actual algorithm, these states are generated as the algorithm runs and does discovery. But for this example, we're going to indicate them here because it makes it quite much easier to follow. And then we're going to add observation vertices. Only 5 of them, as once our robot begins execution, because of the structure of these paths, it will never revisit this first leftmost point to distinguish them. You just have to trust me on it. Okay. Oops. There we go. So let's trace our 2 paths once more on this new graph structure that we're inventing. So first, we trace the top path. And you see, as we follow through this, we build an association between these states in this I-graph. And then, as we trace the bottom path, we are going to realize that these are the same states, but they are connected now differently because we have visited them in a different order. So this ultimate object we end up with tells us these are the recognizable states of the world, these 7 squares. And this is how parts of the plan move between them. But we've eliminated the structure that separated them out into an S movement and a Z movement before, the zig and the zag. Now all we know is there's some plan out there that was at this one state and it took an action and now it's at a different state. So what we see now, is that cycles that previously only existed conceptually are now actual cycles on this graph that we've constructed. And that makes this a much simpler problem. It is much easier to find cycles in a graph when they actually exist. And all we need to do is eliminate some subset of these cycles to obtain a new graph without them. So we can do this, and the algorithm does this. It enumerates all the different ways you can break these cycles. As you might see that, for this cycle, it has 1, 2, 3, 6 edges. You can choose any number of ways of removing those. Some of them will be planned, some of them will not. But what you actually get as an output to this is, well, we eliminated the link initially, like I said, between the plan structure and the world. So we get this grab bag of actions. And these will form the foundation for the actual output, which is a lot of different children, each of which choose some subset of these broken cycles. So we have, just for example, these 3 children here. I think in the actual problem, there's 5 or 6 you can get, but I chose 3. It was easier to look at. So we take this planning problem and this plan, we feed it into the algorithm, and we obtain these 2 things. We obtain this I-graph, which makes explicit any cycles in the graph, and we obtain this sort of operative action set, this grab bag that we're allowed to choose from to make new plans. Oops, sorry. And then the second part of CLIP takes this grab bag and it produces children made from these actions. None of these children have cycles. None of them are like supersets of each other. They're all distinct descriptions of behavior. And all of them have progress measures. So here's these 3 slightly bigger. CLIP as an output gives us these sets of plans that solve the planning problem and have progress measures. It's important to note that they do not necessarily produce the same executions as the input plan. We'll come back to that a little bit later, but they do all perform behaviors that were prescribed by the original plan. So how do we actually take this and translate it into a sensor? Well, now we get to do what we saw Erdmann do previously. We can define these areas for each different type of movement where that movement makes progress towards the goal. So we end up with all these different descriptions. And finally, we end up with a partition like we saw before. So we have a relation between observations, which came from regions of the world, and actions, which define this partition on the world. We can take a subset of the actions for this plan on the left and make these simply regions that prescribe a single action. And we call this a singleton action-based sensor because it prescribes a single action. So at a specific location in the world, this is the only thing you need to know, is you're in go east land, go northeast land, go southwest land. That's it. But as you just saw, I just took some arrows off of this plan, and we wanted to keep the arrows. So we also have what are called permissive action-based sensors, which, as the name implies, permit multiple actions. So you have these original areas we saw before, but now we have these multicolored areas where you can take different actions. So now you can either design a robot that only recognizes one of these actions, recognizes both of them. It depends on the behavior you're seeking. And this is a little bit weird because this is a bit more how we think of a sensor being, right? You expect to take a sensor, you put it in a certain place in the environment, you expect to get a reading. You don't expect to get multiple readings that really correspond to the same point. I mean, there's noise and things like that, but ideally, you expect your sensor to tell you the same thing from moment to moment, rather than having this notion that there's multiple equally correct things the sensor could be telling you. So that's just that's a little odd. It's a little different, and I just highlight it to point it out because it is different from how we typically conceptualize sensors. So now we finally have action-based sensors defined from arbitrary plans, and we can even use them to form partitions on the environment. But these can not only be used to define these sensing requirements, they can also be themselves expressed as reactive plans. And we call them flower graphs due to their shapes that kind of look like flowers. But these flower graphs are both plan and sensor. They highlight regions that have to be kept distinguishable for successful task execution, but they also indicate what action should be taken once those regions are identified. So far, we've taken arbitrary plans without progress measures, and we've broken them apart into plans that do. However, that's still plans that are purely reactive and plans that can be expressed in purely reactive ways. But often robots don't have knowledge to be fully reactive. Often they need to learn things about the world, and that may require them to revisit the same locations over and over again until they have sufficient information to actually identify and reach their goal. And we can't really eliminate that just by eliminating cycles, because that isn't, while it is physically revisiting the same state in the world, the robot's knowledge is changing, and that's an important part of the solving process. We also might just want to maintain the diversity of our planned behaviors. So we took that S and Z plan and we chopped them up into a bunch of things, but none of those actual outcomes can execute the original plan that we had. And so we've still lost something here. And to get it back, I'm going to have to introduce a little bit more machinery, so bear with me. For a moment, let's consider this slightly different world. It's not a p-graph, it's slightly easier to manage. We have circles. These circles give off colors as observations. So you have blue or yellow or this kind of pink magenta, and the robot takes an action, either we'll call them left, right, and forward. These actions are non-deterministic. You can see from S1, if you take the action L or left, you can end up in both S2 and S3, which both give you the observation yellow. If you continue the sequence along, you'll end up in S8 and S9. You'll have no idea which one you're at. And what's important here actually is just understanding that we can make this relation precise. So we can take these history strings of observations we've seen and the actions we took in response, and we can define exactly where we are in the world after doing so. And we call this a trace. So in the example we just saw, executions could end in either of two states, which we can't assign a value to under our current definition of a progress measure. So what if we just assign values to sets of states? What if we use these traces and their outcomes and we put a function on that? So that's what we did. So here's our example again. You can see we have these traces now, these executions, which are down and right and back. I omitted the observations because it makes it a little clearer to read. But you can see here that now on these different observations, we can have these real valued functions. But these, if they were non-deterministic actions, you would see that these would be applied to sets of state. So for example, for this one here, if we tried to go down and to the right, and we could end up in one of these two sets, we could then apply a value onto that set of states rather than the individuals. And we call this an execution progress measure. It's defined on these traces, on these outcomes of execution histories. Like our original progress measures, it takes a value 0 at the goal, and things that come before should have greater values than things that come after. We want to always be making progress. Our original definition is a vertex progress measure. In the way we've seen it up to this point, it has all the same requirements as you saw previously. So what we actually see what we actually see is if we look at our plan that we saw previously, we had this kind of faux structure with these two branching paths. And this structure of this plan allows the robot to remember which action it took before. It commits it to a path and it stores that choice in this branching structure. But each of these individual paths has an action-based sensor that can be defined on it. So we have reactive behaviors on each branch that are separated by a transition that enforces consistency. And if we want to keep that consistency, we need to keep some of that structure. As we saw, by trying to combine them, everything falls apart. You end up with these other plans that don't do quite what we want. So when choices impact future decisions, context matters. When I say context, I mean what robots are remembering. So one way to think about this problem is that robots are often, in an immediate sense, executing something reactive. They have controllers that make a motion, and they control that motion, and then they reevaluate the world, and they take a new action. But the choices that are made that switch us between these decision points are quite important. So going back to this example one more time, like I said, these two paths can individually be assigned action-based sensors, which we express in flower graph form. But what if we want to keep both of them? We can add here, for example, an observation that takes a null observation. Maybe this is just when we start up, we say, okay, quick, make a decision here. We take this action that non-deterministically transitions to one of these two action-based sensors. This transition left or right encodes a single bit of state, that of which path our robot decided to take. And that is actually all the state this robot needs to solve this problem. This robot needs one bit to remember what choice it made, and that is all. So by breaking plans apart, not only into action-based sensors, but also into these reactive segments with transitions between them, which we call vine graphs because they're flowers connected by branches, the robot can very precisely have expressed how much memory it actually needs. And more importantly, if we go back, we see that this choice occurs before this robot even makes a decision. But if we had another type of plan where we branch from here to another flower, we would see specific actions that require memory. So when robots make actions that require then them to remember that they took that to impact their future actions, you would see additional branches. And you'd end up with a structure more like this, where they're connected with each other. So in summary, through the algorithm clip, we can identify plan features that prevent us from defining action-based sensors and remove them. This generates a family of derived plans, each of which imposes a unique partition on the state space, which allows us to define both plan and sensor. And we can also determine when state is required and construct vine graphs, which control transitions between purely reactive behaviors. So that was a lot, but I'm gonna go through some examples now to hopefully make it a bit more concrete. So throughout this presentation, I've claimed that action-based sensors and plans allow us to design robots, right? And they can be useful to designers. So I'm going to go through a couple examples that should help clarify any questions you might have, as well as demonstrate how it can actually be used for design problems. So to begin, we'll start with a very classic problem in robotics, gripping a part and putting it into a known configuration. The main point of this example is that in the previous section, each state in the planning problem corresponded to a single point in the world. However, an arbitrary object can start in infinite configurations, and we're capable of managing that. So again, assume we have a robot that is a simple gripper claw. This robot can close the claw on an object, in this case a 5-sided polygon, and it continues to close until it meets resistance. The robot can also rotate the object 30 or 45 degrees and then apply another squeeze operation. Our part, when squeezed, will actually settle into one of 4 stable configurations, plus their symmetric counterparts. So while we start this problem with an infinite possible number of potential part configurations, the state space actually rapidly reduces in size, but it will never reduce down to a single state. It only reduces down to symmetry. So this problem can be solved completely without the use of sensors by executing memorized sequences of squeezes and rotations. And one example plan for it looks like this. So in this p-graph, we can see that the resulting plan we've designed has both uncertainty and state. For example, the first action on the left corresponds to an infinite number of configurations, as well as multiple different paths which can be taken. We see here that there's a branch depending on if the robot rotates by 30 degrees and squeezes or 45. This is nice that we can do it without any sensors, but it requires that the robot execute this entire sequence of actions every single time it wants to move a part into a known configuration. It also requires storing this entire sequence and remembering where you are in it while you're doing it. And if anything moves the part during your execution, the robot has no way to tell, and it just has to start over again, which isn't very nice. So let's consider that we want to examine the impact of augmenting this robot. And we don't want to give it anything fancy. We simply want to know, after it's done squeezing, whether the gripper has closed beyond some threshold or remained open beyond some threshold. And by some threshold, I actually do mean the height of C. So either the gripper has closed and it's pressed down to the width of C, or when it's finished pressing down, it's larger than that, which corresponds to one of these other states. So what we see in such a case is that an action-based sensor now exists. And our plan actually just looks like this. So this is a purely reactive plan that only uses the current state of the sensor. And we can evaluate the impact of the introduction of the single sensed feature, this in this case just being how far open the gripper still is once it's done squeezing. And it can reduce this problem down into one in which we require no memory of prior action, but which is also now more robust to perturbations or issues that arise during the squeezing. So for another example, we can also use this framework to examine how changes to the world and the available sensing information impact the operability and requirements of a robot over time. So imagine that we're getting to design a robot, a rover. It's going into space for reasons that I am sure are obvious. Once it's up there, we won't be able to fix it if it breaks. So in addition to ensuring that our robot is capable of sensing all the information it needs and performing all the tasks we want it to do, as designers, we'd also like it to have as long a lifespan as possible. For example, by retaining functionality even in the face of partial component failure. Now, this is a very complex system, so let's just focus on a single subproblem, which is that of power management. So our robot has several sensors that monitor its power consumption and its current battery levels, and it can temporarily shut down systems that are drawing too much power. Additionally, we have solar panels, which can be used to charge the batteries. To assist in the operation of these solar panels, we have a couple other tools in our toolbox. We have sensors for light direction, current sensing for how fast the batteries are charging. We can detect the position of the sun through the light sensors. And we have a set of motors, which we can use to fine-tune the position of our panels to maximize our light exposure. So this is sort of our set we're looking at. And then there's a few other things in here that are helping support these features, which we'll come back to. Now, while continually pointing our robot solar panels towards the sun might maximize the charging current for the batteries at all times, it restricts the bearing of the robot, and it requires repositioning and spending cycles calculating where the sun is and all this stuff. So let's propose a power system that reacts to energy demands and the current battery level instead. So while this power management will go on for the entire lifespan of the robot, we can still describe this problem as a task with a goal, where the goal is to have a balanced energy profile. So to start, if power demands are really high on our robot, we might want to prioritize keeping our battery topped up so we can have this sun following behavior where we're constantly trying to maximize the input current that our robot receives. But if the battery is at a decent level and our power demands aren't too high, then it might not be worth it to do that. And we might just want to lay the solar panels flat and collect the sun from whatever angle it's at, and that's our lot. Meanwhile, if the battery is critical, no matter our load, my bad. If the battery is critical, we might want to shut down non-critical functions until we're in a more stable state. And finally, if everything's balanced and it's nice, then we consider ourselves good. We put this to the side until the next time we check our systems. Oops. Sorry. So that's all good. But the action follow the sun implies our robot has the ability to identify the direction of the sun. We assumed that we had light sensors that could figure out where the sun was and point towards it. But what happens if this ability fails? Our robot now has to develop new behaviors to cope with these high loads, where previously it had this much simpler controller. So to implement an action such as following the sun, like I mentioned previously, we need to have the ability to actually move our solar panels. And to identify power consumption in relation to battery load, we need to have had the ability to sense input current from the solar panels in the first place. So we're going to take advantage of those now to develop a new behavior. So here's our plan from before, but now when we have high consumption demands, a different behavior happens. Our robot tilts its panel all the way to the left. So now we have a branch in behavior as we search for the position of the sun based on incoming current. Our robot tilts its solar panel to the right until it reaches some pre-specified threshold. And then once this threshold is reached, we know that to the best of our ability, we're facing the sun and we can resume our normal operations. So now we see that because we've had a change in our ability to sense things about the world and about our own state, we've developed, instead of a purely reactive behavior, we have now developed a behavior that requires state, and we end up with a vine graph. However, we also are capable of still returning to the original reactive behavior when we don't need to retain this information. So with that out of the way, in conclusion, what's the final message? I've talked about a couple different things, but robots and how they function are intrinsically linked into the way in which we design them. Being mindful of a robot's intended purpose leads to robots that are good at their jobs. They're robust, they're fast, they're designed to specification. And while technology changes over time, the fact that robots gather information and use it doesn't. So information-based approaches and focusing on that information we gather and how we use it creates methodologies that are timeless in relation to technology that rapidly changes. And if you take nothing else from this, plans are a statement of desired behavior, and we really don't consider them enough as something that is a statement about how robots should behave. We often consider them as things that we've gotten, and we like that we got them, and then we use them, and it's good. But there's a lot more they can tell us, and they can be extremely insightful for design problems. So that's the end. If you want to read more, okay, A, thank you. B, if you want to read more, here's all the papers that were cited in this. And also I'd like to thank Dylan, who was my PhD advisor and helped a lot on this work. And I'll take questions now, but also I'll go back to this so you can stare at these papers and think about them. So thank you.